Welcome to this explainer. Today we're cracking open the universe's invisible rulebook, Newton's three laws. It's kind of like a cheat code for reality. You know, whether you're sliding down a slide at your local playground, kicking a soccer ball in the backyard, or watching a massive rocket launch into deep space, absolutely everything around us is playing by the exact same three invisible rules. They are the ultimate key to understanding how things move. And I promise, by the time we're done here, you're going to see the world in a completely different way.
Okay, let's dive into this with a situation you've probably dealt with 100 times. Imagine you're at the supermarket. Why is it so much harder to push a cart that is completely stuffed with groceries compared to an empty one? I mean, it seems like a really simple observation, right? But the answer to this question actually unlocks the fundamental physics of our entire reality. To figure that out, we have to start with the first rule of our invisible rulebook. That brings us to Law 1, the lazy law, also known as inertia. Basically, objects in our universe are, well, inherently lazy. They just want to keep doing exactly what they're already doing, and they absolutely refuse to change their behavior on their own.
Now, what's really interesting about this is if you think about some pumpkins just sitting quietly out in a field, because objects are naturally lazy, stationary things like those pumpkins are perfectly happy to just sit there forever. They literally will not move a single millimeter unless an outside force, what scientists actually call an unbalanced force, comes along and pushes them. No push, no movement. It really is that simple.
But wait, there's a flip side to this laziness. Just like resting things want to stay resting, moving things want to keep moving. If you slide a book across a table, you might think it naturally wants to stop on its own. But actually, scratch that, it doesn't. The only reason it stops is because an invisible force called friction grabs a hold of it. If you completely removed friction and air resistance, that book would slide in a straight line at the exact same speed forever. It's just too lazy to stop. This universal laziness actually has an official scientific name: inertia. It's the tendency of an object to resist changes in its velocity, whether it's in motion or entirely motionless. The famous scientist Sir Isaac Newton first wrote down this law way back in 1687 in a book called The Principia. He realized that this innate behavior of matter is basically a universal power of resisting change. Which brings us to the second rule of the universe. If everything is so hopelessly lazy, how do we actually get things to move, stop, or speed up? How do we overcome that inertia? Well, that brings us to Law 2, the heavy push, which scientists call force. And this brings us right back to our supermarket cards. If you want to make an object accelerate, meaning you want it to speed up, the amount of push you need depends entirely on how much mass it has. An empty cart has very low mass, so a tiny little push gets it zipping down the aisle. But a cart loaded up with milk, heavy cans, and potatoes, that has a lot more mass, which means it has a lot more inertia. You have to push it much, much harder just to get the exact same acceleration. Newton neatly wrapped this whole idea up into one of the most famous equations in all of science: F equals ma. Force equals mass times acceleration. In perfectly simple terms, this just means that the force you need to apply is equal to the object's heaviness, its mass, multiplied by how fast you want it to speed up.
Let's look at an incredibly fun, kid-friendly example. Think about kicking a soccer ball. When you kick the ball, you exert a force on it. According to F equals ma, if you give that ball a stronger kick, meaning you're putting a larger net force on it, it's going to accelerate much faster and travel a lot further down the field. The mass of the ball stays exactly the same, so increasing your force directly increases its acceleration. Makes sense, right?
Now we arrive at Law 3, pushes come in pairs, which is all about action and reaction. Honestly, this might be the most surprising rule of all. We've talked about objects being lazy, and we've talked about how to push them. But the universe has a strict policy. Whenever you push on something, that object pushes right back at you.
And this brilliantly illustrates the concept. Think about an apple sitting quietly on a table. Because of gravity, the apple is pushing down on the table with its weight. That is the action. But the table isn't just taking it, it is actually pushing right back up on the apple with the exact same amount of force. That's the reaction. If the table wasn't pushing back, the apple would crash right through the wood. Newton phrased it perfectly. For every action, there is an equal and opposite reaction. In this universe, a single, isolated push simply does not exist. It's impossible. Forces are always mutual interactions between two different objects. They always operate in these perfectly matched tag team pairs, acting in opposite directions. That brings us to our final section, the rules in real life. So we have 3 simple rules. Objects are lazy, heavier objects need a bigger push, and pushes always come in pairs. It sounds simple enough for a kid to master in an afternoon, right? But these rules aren't just for pushing supermarket carts or looking at pumpkins and apples. They are the absolute bedrock of modern engineering.
Let's move into the real world and see how this builds into real-life aerodynamics. Organizations like NASA rely on these exact 3 laws to navigate the skies and explore space. When a model rocket launches into the atmosphere, it's overcoming its resting inertia. When the wind shifts and a kite changes direction, that's an unbalanced force changing its acceleration. And a jet engine producing thrust backward to move forward, that is the ultimate example of the 3rd law. The engine blasts hot exhaust gases violently out the back. That's the action. The equal and opposite reaction is a massive thrusting force that propels the giant airplane forward through the sky. Once you know these 3 rules, your own room turns into a physics laboratory. In fact, think about where you are right this second. As you sit there, your body is pushing down on your chair. So I'll leave you with this question. What invisible forces are pushing back on you right now? Feel that upward push from your chair. That is the universe's rulebook in action, literally holding you up. Keep looking for those invisible pushes and pulls everywhere you go.